So, Jai Hind students, so this is our third lecture in the complex lecture topic series, and the topic for today's lecture is asynchronous counters. So, these are the contents of today's lecture: concept of counters, and concept of counters, counters with mode equal to 2 raised to power n, mode not equal to 2 raised to power n. So, counters are basically sequential circuits which are capable of performing counting operation. Okay. So any sequential circuit which can count, what it will count? It will count the number of clock pulses entering the circuit. So count the number of clock pulses. Counting operation can be either in form of up counting, that means 0, 1, 2, 3, or in form of down counting, or we can say that reverse counting. Okay. So this up counting can also be termed as counting operation, and this down counting can also be termed as timer operation. Okay. So in both the cases, the step by step, clock by clock transition will be either in upward directions or in downward directions. Okay. So there are two types of counters: asynchronous counters and synchronous counters. So asynchronous counters, this is very much clear that one flip-flop can deal with only one bit. Okay, so if we are having multi-bit counters, let's say we are having 3-bit counter. So for 3-bit counter, we'll be requiring 3 flip-flops. For 4-bit counter, we'll be requiring 4 flip-flops. Now all the flip-flops present in the circuit, if they are not having a common clock, okay, that means each flip-flop is having a unique or a different clock connection, then they will be termed as asynchronous counter. And in case if all the flip-flops present in the circuit are connected to a common clock, then they will be termed as synchronous counter. Okay. By synchronism we mean that all the flip-flops will be working simultaneously. But in case of asynchronous counter, it will be clock dependent operation. If the flip-flop will get the desired clock, it will work. If the flip-flop does not get the desired clock, it will not work. Okay. So coming to the asynchronous counter, which is the topic for today's lecture, to design a mode n counter. Now first thing is, what is this mode? So mode means number of unique stages a counter goes through. Okay. So mode is also known as the modulus, and it is number of unique stages offered by a counter. For example, mode n counter will be providing us n stages, and it is also known as divide by n counter. Okay. So we can say that mode 8 counter will be same as modulo 8 counter or divide by 8 counter. Okay. And next thing, this mode 8 counter, that means there will be 8 stages. 8 stages will be 0 to 7. Okay. 8 stages can be 0 to 7. So if I write binary, in binary terms, 0 will be 000 and 7 will be 111. So from this I can see that maximum number of bits is equal to 3. So this mode divide by 8 counter can also be termed as 3-bit counter. Okay. So these are all basics of the counter, how this mode is related to number of bits, how many bits, how many flip-flops, what is the mode. So if I say that mode 16 counter means there will be 16 stages. What will be these 16 stages? 0 to 15. 0 to 15, if I write in binary, it will be 0000 to 1111. That means maximum number of bit requirement is 4. So that mode 16 counter can also be named as 4-bit counter. Similarly for any other mode. Okay. So now some basic things. Number of flip-flops required will be dependent on the number of bits in the maximum count. As in this case, the maximum count was 7, which has 3 bits. So that's why this counter is known as the 3-bit counter. Okay. Now coming to the operation of the counter, whether we want to act like a up counter or a down counter. So if I use negative as triggered clock in the flip-flops, that means if I use negative as triggered flip-flops, I can easily design up counter. Similarly, if I use positive as triggered flip-flops, I can easily design a down counter. Next important thing, only T flip-flop can be used. Okay, only T flip-flop can be used to design an asynchronous counter, but that thing is very much clear to us. The T flip-flop is derived from JK flip-flop by connecting J and K, and connecting J and K, that means shorting J and K. If I short J and K, that JK flip-flop becomes a T flip-flop. So in case examiner asks us to prepare the counter using JK flip-flop, first we have to convert that JK flip-flop into T flip-flop by connecting J and K. Then next thing is all T inputs are connected to logic 1. That means how many, be it number of three number of flip-flops are there, 4 number of flip-flops are there, all the flip-flops and all the T inputs of all the flip-flops will be connected to a common point, and that common point will be connected to logic 1 or a high signal. Okay. Then dedicated clock provided only to LSB flip-flop, the least significant bit. Now counting will be generated. Now if we see this is the count, this 1 is my MSB and this one is LSB. So we are saying that the flip-flop which will be generating this least significant bit will be provided with an external clock by the user, and rest of the flip-flops, all other flip-flops, will get their clock from previous flip-flops output. That means the flip-flop on the left to the flip-flop under consideration. That means second flip-flop will be getting its clock from the first flip-flop output. Third flip-flop will be getting the clock from second flip-flop's output. So these are some common points regarding asynchronous counter. Whatever the mode be, whatever the kind of operation be, either it is up counting or down counting. So these are some common points which we need to keep in mind while designing a counter. So now let's design a mode 8 asynchronous up counter. Now one more thing, asynchronous is also known as ripple counter. Okay, asynchronous is also known as ripple counter, and up counter, that means mode 8 means 8 stages. Okay, 8 stages will be 0 to 7, and up means 0, 1, 2 up to 7, and in binary format ripple 0 to ripple 1. So from here we can see that the maximum number of bits that are required to design a mode 8 counter are 3 bits. So 3 bits means 3 T flip-flops. So we have taken 3 T flip-flops, T flip-flop A, T flip-flop number B, and T flip-flop number C. Now as we have mentioned it, LSB, that means this terminal will be provided with the clock by the user. There will be manual pulses, and rest of the things, as we have mentioned in our slides, that all these things, all the T inputs will be connected to a common point. So let's connect these T points, this, and this thing. All these T are connected, and they are connected to logic 1. Okay, so all T inputs are connected to logic 1. Then we go to know about the clock connections, that least significant bit will be getting the clock from the external input here. Okay, and rest next flip-flop, this flip-flop will be getting its clock from the previous flip-flop output. Similarly, this will be getting the clock from previous flip-flops output, and count these outputs are also be going to used as the count display terminals. So here my count will be displayed. I can connect 3 simple LEDs here QA, QB and QC. Okay. So these are the connections for mode 8 asynchronous counter. So let's check the operation now. Initially, let's say QC, QB and QA. Now that thing you have to keep in mind. While designing the circuit, we have placed LSB first. That means this QA is the first output. But while writing the counting, we have to be very much aware that first we have to write the MSB. So that's why this QC has been written here, which is the MSB, and this last rightmost bit is my LSB. Okay. So the sequence of flip-flop is reverse compared to the sequence of these outputs while writing the counting. Okay. Now let's say initial state is this, when we have not applied any clock and all the outputs are 000. Now let's say I apply the first pulse. Okay. So this first pulse is applied only to this LSB flip-flop. That means this A has been provided with this LSB. This will be getting clock always. This will always get the clock from the user. Okay. So this first clock is provided to flip-flop A. Now this T flip-flop is already connected. The T input of all the T flip-flops are connected to logic 1. That means these flip-flops are just waiting for clock, because T is equal to 1. Output of flip-flop will toggle on the next clock pulse. That means whatever the output of this flip-flop is, it will get toggled if it gets the clock pulse. Why? Because T is equal to 1. That's the truth table of T. If T is equal to 0, output will not change. If T is equal to 1, output will toggle. So T is equal to 1. That means all flip-flops are already connected in toggle mode. They are just waiting for the clock pulse. And this we have said that this flip-flop will be always be getting the clock because it is being provided by the user only. Okay. So this 0 to 1, the output of flip-flop T flip-flop number A, first flip-flop, A flip-flop, it toggles. Now this 0 to 1, this 0 to 1, this 0 to 1, you can see that 0, 1. That means this is positive edge. Okay. So this is positive edge. And the requirement we have already said, this clock symbol, all these clock symbols are of negative edge. Okay. These are all negative edge clocks. So here we can say this is positive edge. That means the desired clock is not available for B flip-flop. If desired clock is not available for B flip-flop, that means output of B cannot change. Similarly, if B cannot change, then C also cannot change. So C will also remain in its previous state. Now coming to the second pulse. Again this second pulse is applied to the LSB flip-flop. So it will again toggle. That means this will change from 1 to 0. Now this 1 to 0 is negative edge. That means B flip-flop, which is connected to this QA. Here this 1 to 0 transition is happening. That means this negative edge transition is available at flip-flop B. So that means B can toggle now. So B has toggled. Now this 0 to 1 is positive. If it is positive, that means C is not going to get the desired clock. So C will remain in its previous state. So this you can see that 0, 0, 0, this is equivalent to 0. This 0, 0, 1 is equivalent to 1. This 0, 1, 0 is equivalent to 2. Similarly, if we proceed further, if we apply the third pulse, again that third pulse will be also be connected to LSB flip-flop. So it will again toggle. This is now positive. Positive, that means B cannot toggle, C cannot toggle. So B and C remain in their previous state. Similarly, fourth pulse. For fourth pulse, again this will 1 to 0. Now this is negative. It is negative. That means B can also toggle. B toggles. 1 to 0. It is negative. That means C can also toggle. So 0 to 1. So in this way we can proceed further. Fifth pulse, again A will toggle. A will toggle. It is positive. Positive. That means further no toggling can take place because negative edge is a requirement. So 0 remains 0. 1 remains 1. Sixth pulse. Again this 1 changes to 0 and this is negative. This is negative. That means B can also toggle. But this B transition 0 to 1 is positive. That means C cannot toggle. So C will remain in its previous state. Similarly, proceeding further, again this 0 to 1 will change, and 0 to 1 is, this 0 to 1 is positive. That means no further toggling can take place. This 1 remains 1, this 1 remains 1. So you can check that 0, 1, 2, 3, 4, 5, 6, 7, all these counting stages are getting generated. And in case we apply one more pulse, you can check here, this 1 to 0 is negative. If it is negative, then it can also toggle. Now this is also negative, that means further it can also toggle. You can check that in the last stage, this and this first one, they are same. Okay, that means if I try to apply more pulses and in a quest to get the next new state, no further new stage can be generated after this 1, 1, 1 state, and it will start repeating from the initial one. So this we can check that this is 0, 1, 2, 3, 4, 5, 6, 7, and again back to 0. So this is your counting operation in upward modes. Similarly, to design a mode-8 asynchronous down counter, you can check here, these clocks are now positive edge. This bubble here, which was here, which indicated this negative edge, is not present in all these flip-flops. That means they can act like positive edge triggered T flip-flops, but connections are the same. All T inputs connected to a common point and further connected to logic 1. Output of one flip-flop connected to the clock of next flip-flop. Then outputs are being used for display. So this becomes the count display. Okay, this is going to get, this terminal is going to get clock pulse from the user, and again connections are exactly similar to the up counter. The only thing is this clock is changed to positive edge instead of negative edge. Okay, so the operation is also similar. Clock, QC, QB, QA. Again, you have to remember that this QC is MSB, this QA is LSB. Okay, initial state we can again assume to be this. For no clock, the output, let's say they are 000. Now the first flip-flop is applied with a clock. First clock enters this circuit. So first clock enters the circuit, so this QA toggles, and this 0 to 1 is positive. Now this 0 to 1 is positive edge. Positive is the requirement, so B also toggles. B also toggles, and this B transition 0 to 1, this is also positive. That means C can also toggle. So this C also toggles. Okay, so you can check that after 0 I am getting 7 on the first pulse. Okay, similarly if I apply the second pulse, again this A will toggle. This 1 to 0 is negative. Requirement is positive edge. That means B cannot toggle, B remains as 1. C cannot toggle, C remains as 1. So this you can see 1, 1, 0 is equivalent to 6. So we are getting the count in downward direction, 0, 7, 6. Similarly, if we proceed further, we will be getting 1, 0, 1, 1, 0, 0, 0, 1, 1, and 0, 0, 1, which is 5, 4, 3, sorry, here it will be 1 and this will be 0, 2, 0, 0, 1 as 1, and last, if this will be the third pulse, this will be the fourth pulse, fifth pulse, sixth pulse, seventh pulse, and again if I apply the eighth pulse, so it will be, it will, again you can check 1 to 0, it will toggle. This is positive. If this is positive, that means further, sorry, this 1 to 0 is negative. This 1 to 0 is negative. Okay, this 1 to 0 is negative. So this is negative. That means no further toggling can take place because requirement is positive. So this 0 remains 0. This 0 remains 0. That means again we can check that this 8th pulse is similar to the first pulse, and the direction which has been seen, observed in the count is 0, 7, 6, 5, 4, 3, 2, 1, 0, and further back to 0 and 7, 6, 5 and so on. So this is mode 8 asynchronous down counter. Now mode 8 asynchronous down counter, another method is that this down counter can also be designed using negative edge clock instead of using positive edge clock. So how is it possible? So for this we have to, the common things which are still the same, I am first making those connections. That means all T inputs are going to be connected with logic 1. So I have connected them with logic 1. Next thing, all flip-flops are going to be taken as count display. So this is also same. Now the only thing that is changing here is that instead of this QA getting connected to clock, I am connecting QA bar to clock. Similarly here QB bar to the clock. Why is it possible? Because whenever this QA and if it generates positive edge, here a negative edge will be generated. And when this generates a negative edge, a positive edge will be generated here. So instead of changing the clock, I am changing the clock connection. Okay. So instead of using positive edge clock instead of negative edge, which we had used in up counter, we had used negative edge, and for down counter we had used positive edge. But now I am saying that down counting operation can also be done using negative edge if I change the clock connection, because by changing this clock connection, the clock is reversed. So this positive edge automatically gets converted to negative edge and negative edge gets automatically converted to positive edge. So this is another option for designing a asynchronous down counter. Okay. Now proceeding to mode 10 counter or a decade counter. Now there is slight difference here. Now mode 10 means 0 to 9. That means 0, 0, 0, 0 to 1, 0, 0, 1. Okay. That means this is not a complete 4-bit counter. This is because the 4-bit counter will be counting from a normal 4-bit. If this would have been a 4-bit counter, so 4-bit counter would have counted from 0, 0, 0, 0 to 1, 1, 1, 1. But I am not interested in counting till 1, 1, 1, 1. I am only interested in counting till 1, 0, 0, 1. Because 0 to 9, that will make my mode 10 counter, or mode 10 is also known as decade counter, or you can also name it as BCD counter, or you can also name it as decimal counter, or mode 10 counter, modulo 10 counter, divide by 10 counter. All these things are same. So mode 10 counter, modulo 10 counter, BCD counter, decimal counter, decade counter, divide by 10 counter. All these counters can be considered identical. Okay. But we have to make some additional connections here. What are going to be these additional connections? First, we will be making those connections which are already known to us, because we are going to design a asynchronous counter. So all 4 T flip-flops have been taken. Why 4 flip-flops? Because maximum counting is 1001, which is requiring 4 bits. So we have taken again 4 flip-flops are there. Again, these things are again the same. That means all T flip-flops will be connected to a common point. All T flip-flops will be connected to a common point. Okay. And this can be connected to 1. Okay. Again, output of first flip-flop becomes the clock of next flip-flop. Similarly here. Similarly here. And there is no further flip-flop, so these are the clock connections. Output will be taken for display. Let's change the color. So this output will be used for display. Okay. I am going to design circuit on the lower side of this these flip-flops, so that's why I am taking these outputs on the upward side. If you have space in notebook, you can also take these outputs in downward direction. So these QA, QB, QC and QD are my count display. Now important thing is that this flip-flop is going to count from 0, 0, 0, 0 to 1, 1, 1, 1 because 4 flip-flops are there. As in previous cases we have, in case of mode 8 up counter, mode 8 down counter, mode was in 2 raised to power n form, mode 8, similarly mode 16. So this 4 flip-flop connection can simply realize mode 16 counter, but we are going to design mode 10 counter. So for this there is a requirement of one more flip-flop input, which we have already studied in our previous lectures or previous topics, that were flip-flops asynchronous inputs, which were preset and clear. Okay, so we are going to use clear here. So all these flip-flops clear inputs are going to be utilized here. So flip-flops clear inputs are active low inputs. So all these active low inputs are connected to a common point. Now if I am able to somehow generate a 0, okay, if I am able to generate a 0 on this terminal, that means I want to clear all these flip-flops by generating a 0 here. All the flip-flops will change their output to 0, 0, 0, 0 at any point of time, irrespective of what the previous output was, irrespective of whether the clock is available or not. So for this, what I am doing, that my counter will start counting from 0, 0, 0, 0 to 1, 0, 0, 1. These are my desired states. Now as soon as this 1, 0, 1, 0 occurs, that means this 1, 0, 1, 0 is not required by me. Now this 1, 0, 1, 0 has to change into 0, 0, 0, 0. So I have to prepare some logic that as soon as this 1, 0, 1, 0 occurs, my circuit is able to generate a 0, and that 0 will be used to clear all these 4 flip-flops. Okay. So what I am doing here, this is my MSB and this is LSB. So you can check that this is QD and this is QA. So you can check here that QD and QB are equal to 1. So I am taking a NAND gate here and connecting QD and QB as input to these terminals. So you can make these connections from here. So QD gets connected here. This QB gets connected here. Now as soon as these QD and QB are 1, 1. So when these two 1, 1 enters a NAND gate, AND gate can produce a 0, and this 0 will be used to clear all the flip-flops. Now it means that for some split of a second or some momentary time, this 1, 0, 1, 0 will be generated, but it will automatically get converted to this 1, 0, 0, 1, 0, 1, 0 will automatically get converted to 1, 0, 0, 0, 0, because as soon as 1, 0, 1, 0 appears, this 1 and 1 from QD and this is QB, sorry, QD and QB, these QD and QB 1, 1 will make the NAND gate output as 0, and this 0 will further activate the clear input of all the flip-flops, and the flip-flop will get, all flip-flops will get cleared, and they will provide 0, 0, 0, 0 output. That means all flip-flops are cleared. That means instead of getting a 10, I am getting a 0. So in this way we can design mode 10 counters. Similarly, if we are provided with any other mode, let's say we are provided with mode 12 counter. If it would have been a mode 12 counter, let's say if it would have been mode 12 counter. So mode 12 means 0 to 11 we are interested. That means 0, 0, 0, 0 to 1, 0, 1, 1. That means these are required, and 12, 1, 1, 0, 0 is not required. That means this 1, 1, 0, 0 has to be converted into 0, 0, 0, 0. That means in that case QD and QC will be connected to NAND gate input. Okay. Okay. As soon as QD and QC become 1, this NAND gate will be activated and it will produce 0 output. So 0 output will be used to clear all the flip-flops, and counting will stop at this 1011, and 1100 will automatically get converted into 0000. So this is all about asynchronous counters. Thank you very much.